Hi guys, Miss O'Connell here. Hopefully we had a nice weekend and that our AP exams went well. Hopefully not many of us need to retake them due to technology issues, and that we feel refreshed and ready to go. Basically what we're going to start with is just a review of everything we've talked about so far with uniform circular motion. That's what we're going to do today. So we're just going to review, take a look at the things that we've talked about so far over the past few class days. Okay, so far we know that uniform circular motion is a special case within circular motion. Okay, so in this case, we have an object that moves around a circular path with a constant velocity. And as we can see in the image to the right, the velocity is tangent to the circle, which means that the actual vector begins on the circular path and creates a tangent line to that circular path. It points in the direction of rotation or the direction of motion. And that vector, the length stays constant. So it means that the speed is constant, but the direction changes at every instant. Okay, so let's say we have some particle, that little black dot. Okay, it moves around at a constant speed around a circle with radius r. Besides just a particle, okay, these objects which we've talked about so far could be a car moving around an exit turn, a satellite orbiting Earth, a ball or a cork tied to the end of a string, even a paint dot on the side of your bicycle wheel. Okay, so uniform circular motion is a special case within circular motion in which the object rotates at a constant rate around that circular path. We know that there are many ways in which we can describe the motion of an object moving in a circle. We can talk about its angular position. Okay, so the amount of degrees or radians that the object has traveled. We can also state the radius of the circle, which is the distance from the center that the object travels. Okay, we can also denote the arc length, which is the path around the circle in which an object has traveled. Okay, it's technically a linear distance because you measure it in meters. We use that variable s to represent arc length. So again, I'll review here. So it's a linear distance that's traveled by an object that moves in a circle. We can determine that arc length by multiplying the radius of the circle, which is the distance from the center to the object's position on the path, by the change in angular position. And theta must be measured in radians. Okay, so we can figure out how far an object's traveled around a path using the arc length formula, which we again measure in meters. Theta must be in radians. Okay, and radians is the SI unit. The equation for that again is S equals R times delta theta, where S is the arc length measured in meters, R is the radius measured in meters, and delta theta is the angular position measured in radians. Okay, rates of circular motion. So far we've talked about its constant speed. So we know that objects move in a constant speed. Even when the radius changes, that speed stays constant, okay, which we saw in lab. We call that speed the tangential velocity. Okay, which is dependent upon how quickly the object moves around the circular path, okay, or the time it takes the object to move around the circular path, which we call the period. Okay, so very similar to the period that we looked at in our previous unit of simple harmonic motion. The period is the time it takes a particle or an object to complete one revolution, which we abbreviate as ReV for rev. And that revolution is equivalent to the circumference of the circle, which we calculated in our last lab, right? Which is 2 times pi times the radius of the circle. So it's how long in seconds it takes an object to move around the entire circular path, aka the circumference of the circle. Okay, that's the period. The tangential velocity, or tangential speed, we use the variable v sub t to represent. Okay, it's the rate at which an object circles around a particular path. Okay, and as we derived earlier, right, it's the distance over the time, aka the circumference over the period. So to find the tangential velocity, you take 2 times pi times the radius, and you divide by the period. Okay, and this is the same equation that you needed to use in the concept builders in order to get those 4 questions right. So if you were confused or having trouble with them, take a look at the radius they gave you and the period they gave you, and make a comparison based on this equation. So the tangential speed is the rate at which an object can move in a circle. It's the circumference of the circle divided by the period. As radius changes, the period changes. The tangential velocity, however, must stay constant. That's the defining characteristic of uniform circular motion. Okay, and this equation here is from the Edpuzzle video. So if you didn't actually watch that video, that might be why you are confused. Okay, so that is from 2 Fridays ago, 2 weeks ago now. The Edpuzzle video explained this equation and did 2 examples. So we're going to go back and do one more example with tangential velocity, just as a review, as we wrap up our circular motion unit. Let's take a look at an example. Okay, so we have a 0.5 kilogram mass attached to the end of a string, which has a length of 1.5 meters. So that means that our radius is 1.5. Our object is going to be whirled in a horizontal circle. So this is a bird's eye view here, say around someone's head. The mass is 0.5 kilograms. This stopper completes each revolution in 0.5 seconds. So that means that it travels 1 revolution, 1 cycle, also known as the circumference of the circle, in 0.5 seconds. Okay, so if it completes 1 cycle in that time in seconds is the period, 0.5 seconds. We're told in the problem that the radius, or the length of the string, is 1.5 meters. So to find the tangential velocity, the constant speed, we take 2 times pi times the radius, and we divide by the period. So I have 2 times pi times r divided by period, We plug in. So we have 2 times pi, so 1.5 meters, divided by the time it takes to make one cycle, which is 0.5 seconds. In your calculator, please make sure to put a multiplication sign in between the 2 and the pi, and then in between the pi and the 1.5. You either need to put the entire numerator in parentheses and then divide by 0.5, or press enter and then divide by 0.5. Your calculator does not know order of operations. You must program it to use order of operations. So if you do not put the numerator in parentheses and divide by the denominator, or you do not press enter and execute this calculation first, you will get the wrong answer. Okay, and I rounded to 1 decimal place as our numbers here in the problem are given to us to 1 decimal place. Okay, so our answer is 18.9 meters per second is the tangential velocity. Okay, again, if we make this radius longer, meaning we make the string longer, the tangential velocity must stay constant unless the force, the centripetal force, changes. Okay, so we're going to use part B of this example to kind of prove that. Okay, so we know that the tangential velocity is a constant rate of 18.9 meters per second. Let's say that we increase the radius to 1.8 meters. So if the radius increases, the tangential velocity is the same. What do you expect to happen to the period? Okay, so hopefully we made a prediction. If not, we'll see in a second. So we're going to take the same equation here. Tangential velocity equals 2 times pi times the radius divided by the period. And we're this time going to solve for the new period now that the radius of the circle, aka the length of the string, has increased. So I'm going to take 18.89 18.9 meters per second and set that equal to 2 times pi times our new radius, which is 1.8 meters. So very, very long string there. And we're looking for our period. To get the period by itself, we need to multiply both sides by t. Okay, and then we're going to simplify. So we simplify, we have left side of the equation stays the same, right side simplifies to 2 times pi times 1.8, we get 11.3097 meters. We divide both sides by 18.9 meters per second to get the period by itself. We got 0.5983 seconds, which we're going to again round to the first decimal place, which would give us 0.6 seconds is the new period when our radius is increased. So what that means, right, if the speed is constant, when the radius increases, the period must also increase at a proportional amount. Okay, so again, if you are having issues with the concept builder, go ahead and take a look back at that concept builder using that equation from the first Edpuzzle video that we just reviewed. Okay, and there's a second alternative example that reviews force, centripetal force as well. So please take a look at that, and as always, take notes.